Okay, so what I want to do today, in this third lecture, is tell you about spectral data, tell you about real slices of the Hitchin vibration. We're looking at the Hitchin vibration giving the integrable system for Higgs bundles, and the first lecture we defined what Higgs bundles were for complex and real groups, and yesterday we saw how to define the Hitchin vibration and the spectral data given the fibers for a few groups. So what we're going to do is keep going with that and see a few parts of what Langland's duality does for this vibration. And then I want to carry on and look at real Higgs bundles. These are one of the branes that we were talking about the first day. And once we look at real Higgs bundles, I want to see them inside the Hitchin vibration. I'll tell you how to think about them in terms of involutions. And we're going to study properties of this vibration and the intersection of the branes. Sometimes we'll still have abelian varieties, sometimes we'll have non-abelian varieties. And moreover, once we do that, then we'll see equivalent ways of defining the other types of branes. So I tried to write here numbers in case people were asking me where to read things from about this subject. So there's a survey of that I wrote, a lecture series that I wrote for Singapore a couple of years ago, which contains the material that we saw yesterday and the one that we'll see today. So the yesterday one was this Hitchin vibration based on Hitchin's work back in '87. The one we'll see today is based on work that I've done in the last 3 or 4 years. So that's for real Higgs bundles. The way that I'm seeing all these things as branes inside the Hitchin vibration and trying to see intersections of these objects, it's based on a few papers with Baraglia, some of them, with Hitchin another, and some of mine. And they are all explained in this 3-page survey, where you can see how the main results fit together. It's only 3 pages, so that might be the best place to start with. And later on tomorrow, when I tell you about other correspondences between branes, we'll be looking at correspondences coming from different representations that we use, or different polynomials, as we were talking, used to obtain the Hitchin vibration, and that's work that I've done with Steve Radler. So let's remind ourselves of the setup. We're going to be working again, as before, with a Riemann surface. Our X will be a compact Riemann surface. And we're still going to look at genus at least 2, and we're still going to call K our cotangent bundle of sigma. And remember that when we talk about GC, it's a complex group inside GL and C for us. So they're all matrix groups. And we're still going to talk about GC in those situations. Other situations can be understood through spectral data, but we won't do it here. So what we saw is that the moduli space of Higgs bundles, MGC, if we put it here, has a natural vibration that sends us to the Hitchin base, AGC, and we saw that in the case of classical Higgs bundles, so let me put with another color what happens for classical Higgs bundles. We saw that here, in the case of classical Higgs bundles, so this is G, L, and C, our Hitchin base was a vector space, which was the sum of sections of different powers of the canonical bundle. So K to the I, for I equals to 1 up to N, for GL and C. And the way that we got it was by taking a representative of an isomorphism class here, a vector bundle, and a Higgs field, thinking of it as a matrix. We took a basis of invariant polynomials, and we applied those invariant polynomials to the Higgs field to get a point in the base. What Hitchin showed is that any base that you take, the same thing works. You always get this Hitchin vibration. You always get a proper map. The integrable system, your fibers, smooth fibers, are compact abelian varieties. So here we have the trace of phi, dot, trace of phi to the N. So one of the interesting things that happens is that the duality between groups, between complexly groups and their Langlands tool, can be seen in terms of the Hitchin vibration. And I'll mention it a little bit yesterday, but I want to emphasize it today, since we're going to be looking at dualities later on too. So for our groups GC, and the ones that we saw yesterday, GCL, we mentioned GL and C, and GL and C. We mentioned SL and C. And we'll talk about PG, L, and C. And the last one that I mentioned a little bit, and I'll go back today, SP to N C. Well, in either side, we're going to put it an SO to N plus 1 C. So if we look at the Hitchin vibration and you apply the invariant polynomials are the same for both groups. And so when you apply invariant polynomials in your moduli space for the Langlands dual group, you'll see that the vibration fibers over the same points. That's important. And a way of checking these, for instance, is by applying or taking the characteristic polynomial of your Higgs field and seeing that they indeed, for Higgs bundles here and for Higgs bundles here, the characteristic polynomial, the coefficients are equivalent. So the dual Hitchin vibration fibers over the same space. And what the Strominger, Yau, and Zaslow conjecture say, so SYZ says, is that the duality between the moduli spaces can be seen in terms of the duality between the fibers. So the fibers, what are the smooth fibers in these cases? So smooth fibers. We saw that in this case, the fibers are Jacobian varieties of the curves defined in the base. And we saw that in this case, we have prime varieties here. And so what Hausel and Thaddeus saw in 2002 is that when you take PGL and C, the PGL and C Hitchin vibration, what you get here as fibers is the prime variety of S sigma, but quotient by torsion points, torsion endpoints. The GL and C case, it's self-dual, so it's good that as a variety is self-dual, Jacobian of S. And there's something interesting happening, and I'll finish the part of complex Higgs bundles by mentioning a little bit about the SP2NC Higgs bundle and what is it dual to SO2NC. So a way of seeing it is the following. When you take GC equal to the symplectic group, SP2NC, and you look at a Higgs bundle, we mentioned that a Higgs bundle E phi has a vector bundle which has a symplectic form. This is a rank, so rank 2n symplectic vector bundle. So it has a symplectic form omega. And the Higgs field is compatible with that form. So if we put omega of V phi W is equal to minus omega of phi V W. What this is telling us is the structure of the Higgs field. So in particular, the Higgs field is off diagonal. And we mentioned that the characteristic polynomial then, so when we do the characteristic polynomial of the Higgs field, which is the determinant of phi minus lambda times the identity, this will be something with only even degrees. So lambda to a 2n plus 1 lambda to a 2n minus 2 plus a to n, where all these are sections very similar to these, except that the odd degrees have vanished. A and are sections of the only even powers of the canonical bundle. So this is our equation for the spectral curve. So when we look at the zero set of this equation, we put a 0 here, this will be a curve, so let's just call it S, like before, and it's a curve inside the total space of the canonical bundle. This is our spectral curve for the Higgs field, and if we wanted to understand spectral data in this case, we need to say what extra conditions do we have to put on line bundles in the Jacobian variety so that we get spectral data for the symplectic group. So the question here is, what conditions we have to put, we add to a line bundle L inside the Jacobian of S, such that when we push down the image, so this is our spectral curve S is a cover, let's put it, this is total space of K, and we are going to call, like yesterday, pi the projection from S to sigma. This is a 2n to 1 cover. So such that when we push down our line bundle, the direct image of our line bundle, which is what we define as our vector bundle, has a symplectic structure. Has a symplectic structure. The reason I want to go a little bit deeper into this case is because when we look at the real slices, many of the cases in real Higgs bundles will have similar conditions. We'll have conditions where we need some structure on the vector bundle. We need the vector bundle to decompose, and we need some kind of symplectic form or other form to appear. And the trick in these cases is to look at a quotient curve. So the trick here is to note that you have an involution that we mentioned yesterday that sends lambda to minus lambda. And when you look at your curve then, in our big picture, what we'll have is a spectral curve S covering 2n to 1 our Riemann surface. We have down here our Higgs field, which has a rank 2n vector bundle with a symplectic form. So that will tell us that we have E here and phi. And what we need to do is we need to look at line bundles here, and we said we were going to look at line bundles here such that when we apply our involution, we are isomorphic to the dual, the dual line bundle. How do we understand this spectral data, or how to understand these fibers? Because it's not good enough for us. We had before that we had Jacobians or prime varieties. It's not good enough for us to just say it's anti-invariant line bundles. So what we look at is we look at the quotient by this involution of the curve, and we look at this other cover. So this is an n to 1 cover. And if we quotient by an involution a smooth curve, this will be a 2 to 1 cover. And the line bundles that are there then are in the prime variety. So the condition on L is that the line bundle L is inside prime of S sigma. Oh, sorry, S little sigma. So the spectral data for symplectic Higgs bundles, the fact that it's self-dual will give you a duality between the vector bundle and its dual that will be associated to the symplectic form. So you'll be able to construct a symplectic form through the action of this involution. Now you may wonder, how does that relate to SO2n plus 1 Higgs bundles? We said that in the duality, SP2n and SO2n Higgs bundles should be dual. And when you look at, when you want to do the duality through spectral data, you need to understand fibers of the two fibrations. So here we gave an overview of what happens with the fibers for the symplectic group, but when you look at the fibers for the special orthogonal group, you might notice something strange, because we were talking about smooth fibers, and if you look at a matrix which is an SO2n plus 1 matrix, and you look at a Higgs field that is compatible in the same way that we ask for compatibility, what you notice is the following, is that for GC SO2n plus 1, there's one eigenvalue of your matrix which is 0, and all other eigenvalues appear in pairs, which means when you look at a characteristic polynomial of such a matrix, you have one term, so or the Higgs field, and this is again just linear algebra, looking at matrices in SO2n plus 1, the Higgs field phi has one eigenvalue 0, and all others appearing as plus minus something, and all others appearing as plus minus. So plus minus the eigenvalue, say E. Which means in the characteristic polynomial, when we do char of phi, we'll have something that looks like, instead of the spectral curve like we saw here, it'll look like lambda outside, giving us the eigenvalue for 0, and then here, the ones that come in pairs, so 2n plus a1 lambda to a 2n minus 2 plus A sub n. And now you start seeing the similarity with sp2n C Higgs bundles, because the spectral curve, this spectral curve is always reducible. So in our notion of the Hitchin vibration having smooth fibers over smooth points, or the smooth loci of the Hitchin vibration, these curves are always reducible, so you have to redefine that notion. And what you will see many times in the literature is that we talk about the smooth loci of the Hitchin vibration depending on the group. So if we have groups like the symplectic group where the generic point is smooth, the generic point here is smooth, and so those are the generic points in the Hitchin base. The generic point here, all the points are singular, the curve is always reducible, so what you say is that the generic point in the Hitchin base is this one. So this is what you call the equation of the spectral curve. So this defines S, and so a generic point in the base. So in this case, it's the first case where you're seeing that actually it's not just taking the characteristic polynomial to get a point in the base. Sometimes you have to do a few tricks. Sometimes you have to take the invariant polynomials and take some of the polynomial that you get, some of the characteristic polynomial. So no, we don't care about anything else but to take. We want to study generic points in this Hitchin vibration. And the generic points, when you look at this linear system, once you ask for that to go away, the generic points are the points here. So what are the properties of this curve? So again, you can use Bertini's theorem to see that this linear system is generically smooth. So use Bertini. Bertini tells you that it's generically smooth. Smooth S. And it also tells you the ramification points are the zeros of AN. And this will come up again later on because the ramification points of your curve are important. So this curve S is ramified over zeros of AN. So what does Langland's duality or mirror symmetry tell us about the two Hitchin vibrations and the duality between the fibers? How can we discern that? Well, in one side we have the spectral curve, 2n cover of the Hitchin base. We take a line bundle that is invariant, and that gives us the spectral data. On the other side, we have always a singular curve, but once we take the lambda away, we have a curve which is just like the symplectic curve. And so what you do to obtain the spectral data for the dual side is you take the spectral data of your symplectic group and you extend that vector bundle, that's a 2n vector bundle, you extend it by the eigenspace for the lambda value. So the idea in this case, and I'm not going to say much more, but I just want to start showing you that there are similarities between the dual groups. The idea here is that for spectral data, in this case, so for spectral data for SO Higgs bundles, SO2n plus 1 Higgs bundles, I should have put a C here, it's complex. The spectral data, take the spectral data inside the prim variety, so take the spectral data for the SP Hitchin vibration, prim of S as quotiented, and now extend in some appropriate fashion by a kernel of this map, and extend by certain kernel. So this is not a trivial thing. I'm just putting a line here for you to relate the two spectral data, but in this is to read about this duality in this case, you have to look at Hitchin 07. And in that paper, he takes like it's a 12-page or 20-page paper, and it's 5 of them are for that. So it's not trivial. You have to do this extension, but by taking a lot of care about the ramification points of this spectral curve and putting this kernel in over a certain number of these ramification points. But you can see relations, and you can see these quotient curves appearing. And these quotient curves will be very useful when looking at real Higgs bundles. Yes? What, sorry? So indeed, so you have, because you have the two components. I haven't seen it in that paper. So you think it should follow from there? Yeah, I'm far from an expert, but so I'm not sure. Yes, you asked me before. I don't know how to get the spectral data for spin bundles, but yeah. No, you in principle get just one, the one corresponding to the component in the identity. Yeah. So you will get, and I'll mention some more about how to look at topological invariants of these spaces from the spectral data. As I think it's a nice way of seeing invariants and inequalities. But you'll see that you can only get some. So there's lots of people working on that from the cameral curve perspective. There's Peter Gothen and Andrea Oliveira who showed that the fiber was connected for SL case. You can think about spectral data so you should be able to by doing this kind of, so this is a singular fiber, right, in our GL. So let's just think about this. We're looking at GL Higgs bundles, and inside GL, we're looking at SO2n plus 1. So in the fibration for our GL, we're in a singular fiber. But that singular fiber, we're okay with it. We can understand it in this way. So there are tricks, and I'll show you one more trick on how to study other types of singular fibers. But there's no, from this spectral data perspective, there's no generic method to understand them. I think the safest is, I'm not even sure cameral covers would work, because cameral covers usually use smoothness. But it would be great to devise a method to do it in a more standardized way. Okay. So I want to look at this duality now, and we know that the duality is there. We know that mirror symmetry tells us about the fibers, but we also know about what it does to branes of different types inside these moduli spaces. So I want to tell you start again with branes, and then carry on today with the type BAA branes, and tomorrow with the other types. And I want to understand them through spectral data, bearing in mind that it has lots of applications, both to understand duality between branes, but also to understand representation theory of the Riemann surface and higher dimensions. So we're going to now choose a real group of a real form of our complex group. So in our setup here, we're going to take a real form. Okay, I'm going to move this away. We're going to call G. So now let me add a little bit more information to this set of Riemann surface, cotangent bundle, and complex group. G will be a real form of GC. So we saw yesterday the examples. We took real groups. What we want to do is understand this real form as fixed point set of an anti-holomorphic involution. So this is fixed point set of anti-holomorphic involution. And because we're taking any real form, let me just call it here sigma. Is anti-holomorphic involution. And another thing that is given to us, so this is a choice that we're making, but once we have our complex group, one thing that we are not choosing is a compact subgroup. So the maximal compact of the complex Lie group will be fixed point of some anti-holomorphic involution. So let ρ be the anti-holomorphic involution fixing the maximal compact of GC. There will be one last thing that we're going to make a choice in a little bit, but let's just look at these two objects. And I want you to look at these two objects for the following reason. If we want to understand Higgs bundles real spaces, or we want to understand subspaces of the moduli space of Higgs bundle, in terms of the integrable system here, what we need to do is we need to somehow see them inside the fibers. And for that, it's very useful to take the approach of fixed points of the involution. So if you want to understand real Higgs bundles, you can either define them like we did in the first day, or you can also do the following, and this is what Hitchin was using when trying to construct the Hitchin component. So later on we'll see what the Hitchin component is, but that was his method of seeing that there was a component for any split real form. He was looking at fixed points of involutions. So we're going to follow those ideas. So look at, if you care about where it comes from, so this is Hitchin 92 in his Heck-Muller theory paper. What he suggested is look at Higgs bundles and look at fixed points of the following involution. If you ask the holonomy of your Higgs field, so you ask of the solutions of the Hitchin equations to have holonomy on the real form, what you have to do is you have to look at an involution that sends E phi, so the isomorphism class, so we're looking at fixed points in isomorphism classes, of sigma rho E and minus sigma rho phi. If you look at fixed points of these will be, so it fixes G Higgs bundles. The same Higgs bundles that we defined the first day. But this is another way of seeing them here, Higgs bundles. So sigma is an involution fixing a real group, and rho is an involution fixing the compact real form. So G is in principle, not to make it boring, it's a non-compact. Non-compact. So you can take SUN and SLNR, and you can take the anti-holomorphic involutions fixed each of these real groups inside the complex. Yes. And sigma depends on which. So if you want to fix SLNR, it's A goes to A bar, right? It's just conjugation. And that's a great question, because if you look at Hitchin's equations in his paper in '87, when studying young meals, he was just putting the star because he was looking at SUN. And that's why it's natural then to just forget about SUN, go to a generic case, and then put the rho here. And that's why we put the rho here. You'll see that most of the things that we are doing, you can generalize in several directions, and one is to take another anti-holomorphic involution. But if you put rho, you recover the solutions to the Hitchin equations. So, okay, this involution fixes G Higgs bundles, and the next thing that we know is that if we look at brans in the moduli space of Higgs bundles, the way that we were trying to do it, yesterday, we said since MGC is hyper-Kaehler, we fix the three complexes, so fix I, J, and K. We said that I was coming from the Riemann surface, and J was coming from the complex group, or the flat connections, and they satisfied the square was minus identity. This is the convention of Schaposnik and Witten, and it's a convention that Hitchin takes in his latest papers. And if you fix those I, J, K, you can have different types of brans. So now look at Lagrangian subspaces giving A brans, and let's use the forget map to forget about the sheaf for hyper-holomorphic line bundle in each of the cases, giving A brans and complex submanifolds, giving B brans. Okay, so what Schaposnik and Witten saw in 2006 is that in their electromagnetic duality paper, you can see that these Higgs bundles are actually an example of what they say is a BA brane. So it's a holomorphic space with respect to the complex structure of the Riemann surface, and it's Lagrangian with respect to the other ones. So today we're going to focus with these brans, but let me tell you how you construct the other ones so that tomorrow when we look at the other brans, we know how they fit in this more global picture. And we'll come back to the picture and to the duality, Langland's duality. But if you call this I1, what we wanted to do with David Baraglia, and you can read more here, is to construct the other types of brains that are available. So yesterday we said that there were A brains, there were A brains, and there were A, B, and B brains. So we wanted to construct other types of brains using similar involutions to what Hitchin used back in '92. And what you can say is, okay, we have put a complex structure on the group. We have a complex group, and we took a real structure on the group. We have a complex surface. Why don't we take a real structure on the surface too? So we're going to consider F going from sigma to sigma, a real structure. So this is an anti-holomorphic involution. Locally, it looks like conjugation. So locally, it's just Z goes to Z bar. And using these other involution is that we can construct the other types of branes. So what are the other types of branes? The other types of branes will be, let me put it here, let me call I2, the second involution, and the second involution, E phi, we'll send it to, now we're going to use our F, rho E, and minus F rho phi. And if you look at the fixed point set of this, it fixes an ABA brane. And if you have three complex structures and you have three symplectic forms, so you may ask, okay, it's natural to have three involutions then, fixing three types of branes. If you compose I, so make I3 the composition of I1 composed with I2, these will be fixing, so fixes an B brane. So looking at these different types of involutions, you obtain different types of branes as your fixed point set. Before we specialize on this case today, let me tell you a few comments about why you would care about these involutions. So these ones are real Higgs bundles. We mentioned that these are representations, these are related, and we saw from Richard's talks already, to representations of pi1 of the Riemann surface to the complex group, quotient by some constant. So let's say that. This one give you representations into real groups. And if you look at this ABA brane, what we'll see tomorrow is that it's related to representations of three manifolds. So there are three manifolds M such that, in fact, what we have is that sigma is the boundary of M. So anytime in principle, you should do it, and you should be able to do it anytime. I'll tell you for which ones this works. You have three manifolds bounding your Riemann surface, and representations of that three manifold will be related to these ABA branes. And this third involution, in fact, what it fixes is this pseudo real Higgs bundles, introduced by Indranil Jacques and Oscar Garcia Prada. So you may ask, how can we generalize these things? One of the ways that this was generalized by Indranil and Jacques and Oscar is, or maybe not Jacques, is by, instead of considering rho, sorry, I can't remember, instead of considering rho here, that we're considering because we're recovering these real Higgs bundles, but most of the properties of these branes come from the fact that you have an anti-holomorphic involution. And that's the main point. So you could put any other anti-holomorphic involution. And if you do it, you get another set. So you get different families of three branes, which hopefully one day will have more applications to see what they relate with. So they are not real Higgs bundles, but there are something related to them. And if you put the compact one, you recover these ones. The interest in these other branes, beyond the three manifold, is that this ABA brane is a Lagrangian fibration giving a real integrable system. So tomorrow we'll see how to understand the components of this brane inside the moduli space in terms of the fibration and in terms of real points of Jacobian or prime varieties. Are we okay? So let me tell you more about this BAA brane. So this brane of real Higgs bundles. We want to understand inside the Hitchin fibration. So we need to understand what is extra information that we're going to add to those line bundles in Jacobian varieties to recover the brane. The first thing that you can ask is, how does this brane intersect the Hitchin vibration? So I want to ask question. How does this brane intersect the Hitchin vibration? So you can ask this question for each of these different branes, and we're going to see the different cases that can appear. Yes, for split real forms. No, it's a BAA brane. Of the Riemann surface. And because you're looking at the real slides with respect to the complex group, you have a Lagrange. Yeah. So I should mention that all these branes, it was also generalized to instantons. So you see the same type of triology of branes appearing from involutions on instanton moduli spaces. This was done by Marcos Jardim and Emilio Franco in Brazil. So indeed, the Hitchin component, the Zech-Muller space, are an example of BAA branes appearing when we take G, the split real form. And we'll see that split real forms are actually quite particular. So when you ask this question, how does the brane intersect the Hitchin vibration, we can come up with different scenarios. So we can ask, okay, does it happen that it has finite intersection? Finite intersection with smooth fibers the vibration, so of the Hitchin vibration. Let me just put smooth fibers, you know of what? Of the Hitchin vibration. So it can have finite intersection. It could have some positive dimensional intersection. Positive dimension, or positive dimension intersection with smooth fibers. But it could also lie completely inside the singular locus of the Hitchin vibration. And this is a very interesting case, and this is where the non-abelianization of the fibers appear. It could lie completely inside singular locus. So what are examples of these cases, and what do we know about those examples, and how do we calculate the spectral data? So let me do that. I have 20 minutes, yes. So when do you have finite intersection of the Hitchin vibration? This happens in particular when you have G equal your split real form. So split real form. In fact, in this case, what I was able to see is that when you look at the fixed points of the involution inside the Hitchin vibration, yes? That's a great question, and depending on the real form, it will either preserve all. So what you have to do is you have to look at the action of your involution on invariant polynomial. So you look at the basis of invariant polynomials. For most groups, it will preserve the basis, which means it lies over the whole base of the Hitchin vibration. However, for the SO2n case, it doesn't preserve the Faffian. If I say the invariant polynomials for SO2n has the Faffian, and only when it's, I think it's congruent to 1 mod 4, it will preserve them. But which means in that case, many times it will lie over some part of the Hitchin base. Yeah. So it will depend, but that can be seen. It's in the chapter 2 of my thesis, if you want to see it. So in the case of split real forms, with the fixed points, in this case, what you get is that the intersection, so the intersection here is given by torsion 2 points, so points of order 2. Torsion 2 points in the fibers. So what do we mean with this? Let's do an example here. So the first example we want to look at is, for instance, what happens with SL and R, split real form of SL and C. We said that for SL and C Higgs bundles, bundles, we have line bundles L inside the prime variety of the curve S sigma. And what we're asking now, we're asking for the line bundle now for SLR. You're asking for the line bundle to be of order 2. Your line bundle has to be square to the identity. And if you want a quick test to try to understand why this is necessary, really, you can go to the first case of this. So you can look at SL2R, and you can see what is the Higgs bundle for SL2R. When you look at SL2R Higgs bundles, a Higgs bundle, E phi, is given by a vector bundle of rank 2, which can actually be expressed as the direct sum of two line bundles, a line bundle and its dual. And your Higgs field has off-diagonal structure 0, beta, gamma 0, sending L to L dual tensor K, and so on. So beta sends L dual to L tensored with K, and gamma sends L to L dual tensored with K. So now I'm making a mixture of letters. All right, let me call it something else because we had already talked about an L there. M. Okay, so it's M plus M dual. It's a line bundle M, so for M on sigma line bundle. So now you're trying to understand what are the conditions on your spectral data on the prime variety that would imply that when you push it down, the direct image sheet decomposes into two line bundles. You know that it's in the prime variety, and because it's a rank 2 cover, what you know is that your spectral curve here is a rank 2 cover of your Riemann surface given by an equation of the kind lambda square minus A equals to 0. This is 2-to-1 cover, and you have line bundles on the prime variety. Because it's a 2-to-1 cover, the prime variety, so note, the prime variety of S sigma is also the line bundles that are sent to their dual by the natural involution here. So here we have sigmas, so you have lambda going to minus lambda, let's go with tau. So you have an involution here that acts, and the prime variety is the set of line bundles such that when we apply the involution tau to the line bundle, we go to its dual. If now we ask for the line bundle to be preserved, if we ask for the line bundle to square to the identity, it means that the line bundle is preserved by an involution. And then when you push it down, you have invariant and anti-invariant sections, and that's what's going to separate the bundle. So when you push it down, so here, you note that L squared is equal to the identity. So L is isomorphic to L dual, which at the same time is isomorphic to tau applied to L. So it's preserved by this involution and the invariant sections. So then, invariant and anti-invariant sections are what give you the composition on M and M dual. And this is just for the rank 2 case, but you can see this for, is there any question? You can see this for higher rank, and you can see this for other groups. So before we finish, I want to tell you a bit more of how that idea of having things that square to the identity or that are preserved by involutions give you the compositions on direct images in the Riemann surface. So this happens when you have positive dimension intersection with the smooth fibers. And an example of this case is, for instance, if you take G, I don't have more yet. If you take G here to be, for instance, the special unitary group with the same signature. So let's say SUMM. If you take SUMM, so these are Higgs bundles which preserve a Hermitian form of signature MM. Okay, special unitary group with signature MM. Those Higgs bundles will have the structure, so the Higgs field, or Higgs bundle, is E, which is the direct sum of two rank M vector bundles. So V plus W, these are rank M vector bundles. And the Higgs field is an off-diagonal Higgs field, 0, beta, gamma, 0, no extra condition. So very similar, it's not surprising, very similar to the rank 2 case, SL2R is SUM11. So what happens with spectral data for this case, and how can we understand it to see that the positive intersection is actually abelian varieties, it's actually Jacobian varieties of some quotient curve? The way that we understand it is very similar to SL2R case. So we look at the point in the Hitchin base, we try to understand this action on invariant polynomials by looking at the characteristic polynomial of a Higgs field that looks like this kind here. So how do we look at this characteristic polynomial? We're going to be looking at G equals SUMM. And when you look at the characteristic polynomial, the determinant of the Higgs field minus lambda is identity. Still in linear algebra terms, what you have is that this is lambda to the 2m plus a1 lambda 2m minus 2 plus am for ai a section in H0 of the even power, so 2i of the canonical bundle. So why is this? It's off diagonal. When you take traces, traces are fine as spaces of invariant polynomials. You take traces of those matrices, odd degrees vanish. The eigenvalues are all coming in pairs. So this curve, the zero z of this curve, defines our curve S inside the total space of the canonical bundle. If you care about the physics perspective, this is what's known as the Seiberg-Witten curve, and what it has is an involution here, just as in the SL2 case, that sends lambda to minus lambda. And this is what you have to use a lot in order to construct quotient curves, in order to construct spectral data. So in our picture, let's compare it. I'm going to leave the picture of SL2R here to compare it all the time in order to see this positive dimension intersection. And hopefully by looking at all these examples of polynomials and spectral curves, you start understanding the type of tricks that you can do with involutions, both on the curve and on the surface, to get the appropriate spectral data. So we have our curve S. It's a cover of the Riemann surface. Let's call it pi. It's a 2m to 1 cover. And we have here line bundles in the Jacobian variety in principle, because they're classical Higgs bundles with some extra condition. And we're asking what is the extra condition that implies that when we go downstairs, we'll have a B plus W as our Higgs bundle with the Higgs field 0, beta, gamma, 0. So this is what we're aiming at the level of the Riemann surface. In order to decompose our vector bundle, we learned that if a line bundle on the curve is preserved by an involution, then the invariant and anti-invariant sections will push down to 2 bundles. So really, that will be the condition that we need to take. We're going to take Higgs bundles such that when we apply this involution, it is preserved by the line bundle. It's preserved by the involution. So we're going to take L such that when we leave the involution to that curve, we are preserved. What are the important facts of this curve? One of the important facts is that this is ramified, just as we said before, over zeros of AM. But understanding the Hitchin vibration as Jacobians or prime varieties has been very useful, and here we don't have that information. We have invariant, yes, sorry. Yeah. Because it's the same thing happening here? Well, it's a structure that if, so it happens for groups, in real groups and in some complex groups of tube type that you'll have even degree. So there will be some underlying structure that is telling you the invariant polynomials that are preserved are only those of even degree. And as soon as you have homogeneous polynomials of even degree, you have an involution acting on your variable. So there is a generic statement to make. I'm not sure that there is a preferred real structure. You could put it in those words, I guess. But indeed, it's something very similar happening because we can take the same way that we did in that case, we can take the quotient curve by that involution, and we take this projection. This is a 2 to 1, and this is now an m to 1. And although we couldn't understand the spectral data, we couldn't go further than saying line bundles preserved by an involution. We can try to express those line bundles in terms of spectral data on the quotient curve. And what you actually see is that a line bundle which is preserved, the set of line bundles preserved by an involution here, it's equivalent to just taking the Jacobian here with some extra information. So the spectral data can either be seen as the set of L in the Jacobian of the spectral curve such that tau preserves the Jacobian, tau of L is isomorphic to L, but also it can be seen as the following, which is equivalent to taking the Jacobian of your quotient curve, and I'll tell you now why, is the Jacobian of your quotient curve plus the choice of subdivisor of AM. So you choose the subdivisor of your ramification divisor, and that together with the Jacobian variety, that gives you the spectral data. So when you're looking at the intersection of this brane with the smooth fibers, you have Jacobian varieties appearing. And how do you understand these line bundles? What do I have? Yes? No, so this is the only condition. This is the only condition that's equivalent. There will be more than that, yes. Will be preserved, yes. So those ones are always there, but there might be others. So be careful with which involution, right? If I pull back, it's not from here, but from here. Anything that I pull back from here to here will be preserved. And that fact will be used many times when you're trying to understand degrees of the line bundles. You'll be using many times that fact. But you also will have things, so there will be some extra data. And that's a great point. And I'll finish with that so that you know why is this extra choice that Johan is asking? Why is there a choice of line bundle here? And the fact going on here is that when you have your Riemann surface, and we're going to have this again tomorrow when we look at the other type of brane, when you have your fixed points, your ramification divisor of your cover, so we have our ramification divisor, and these are the zeros, 0 of AM. When we have the involution acting here, tau, it has fixed points, and the fixed points are the ramification divisor of our curve. Over here, we have line bundles. We have the line bundles over everywhere, but in particular, over those fixed points, you have a one-dimensional space that is sent to a one-dimensional space, which is itself, but it could be sent by plus or minus 1. So over each point here, once I give you an involution, and I give you a line bundle, and I tell you your line bundle is preserved by the involution, there's an extra piece of data that you have to tell me, which is, what is the isomorphism? So here I'm being cheeky by not telling you what isomorphism I'm taking. I'm telling you it's isomorphic, but there is an isomorphism. That isomorphism will be labeled by a plus or minus 1 over each point. This plus or minus 1 is this choice that I put here of a subdivisor. We just choose the -1 or the +1s, but those will be the choice. And moreover, by looking at this action at the level of the spectral curve, this is our spectral curve S, you can recover the topological invariance of the Higgs field, so you can recover the Toledo invariant and the bounds, the Milnor-Wood type inequalities, from this action and these plus or minus ones. Because this choice of subdivisor, the subdivisor will have a degree that will be related to your Toledo invariant, and because it's a subdivisor, it will be bounded by the number of ramification points that will give you your Milnor-Wood type inequality. And this will happen for all groups, as I was suggesting, all groups of tube type, although it's been done for just some of them. So I'll stop here, and tomorrow I'll tell you more about how these spectral data and this method of looking at involutions on the spectral curve, on the Riemann surface and fixed points tells you about the branes of different types. Thank you. Yes, there won't be of degree 0. Yes. And actually, the degree 0 case will be more difficult to understand than. So what you're requiring for SL2 is that the determinant has degree 0. And it won't indeed be degree 0, and the degree will depend on the number of points where your involution acts as -1. Yeah. Thank you.